Hi, I'm Vijita Pal from Cornell University, and today I'm going to present my work on similarity models of passwords built using neural networks. The number of password breaches have increased over the years. Millions of passwords are leaked every year. According to a recent report, in the first half of 2018 alone, about 4.5 billion records were exposed. With the increase in the number of websites and users, password breaches will become more prevalent in coming years. These leaked out passwords are often compiled and sold over internet. Attackers use these compiled leaked datasets to attack other websites. In this example, the attacker tries to log into Mark's account in some other website using his leaked password. On the other hand, Mark has reused the password on the other website. This is actually a very common phenomena, as prior work suggests that 40% of users reuse passwords across websites. Thus, it is very easy for the attacker to compromise the account by just directly using the leaked out password. This kind of attack is known as credential stuffing attack, and it's the most prevalent form of attack, prevalent form of account compromise today. To prevent these kinds of attack, websites nowadays integrate their authentication system with breach notification services that inform the websites about new password breaches. Thus, when the website comes to know that Mark's password has got leaked, it notifies Mark about it notifies Mark to reset his password. Mark then goes to the website and changes his password, which then stops the credential stuffing attack. However, the attacker can still try out a different kind of attack in which he tries out, in which instead of trying the exact leaked out password, he tries different variation of the leaked out password. And since Mark has selected a very similar password by changing the suffix 1 to suffix 123, the attacker is again able to compromise his account. This kind of an attack is known as credential tweaking attack. And in this paper, we developed the most damaging credential tweaking attack using deep learning techniques. We found out that this kind of an attack can compromise 16% of accounts in less than 1,000 guesses. We also evaluated the efficiency of these kind of attack on real-world authentication system by performing a simulated attack on user accounts of a large university. We then proposed the first ever defense against credential tweaking attack, a personalized password strength meter built using neural network-based embeddings. These kinds of password strength meters are able to stop all known credential tweaking attacks, and it is fast and lightweighted for production level deployment. So the starting point of our work was the fact that now we have lots of information on how users select passwords from large number of leaks posted publicly. We used a leaked data set that we found online, which contains billions of username password pairs. We cleaned and merged our data set to get a list of passwords for a given user. The point was to get lots of data on how users select similar password. We noticed that there exist similarity patterns between the password of same users. For example, users often append 123 to their current password to generate new password. We also noticed that 10% of distinct password pairs of the same users are within edit distance of 1. Prior work manually curated transformation rules using these kind of similarity patterns. However, this kind of approach has its own limitation, as new guesses cannot be generated once the rules are exhausted. Also, one might miss some subtle similarity patterns. For example, if a user adds or replaces a character in between the password, then, excuse me. Yeah, so if it adds or change a character in between of the password, then the, I'm sorry, in between of the password, then the manually chosen transformation rules may overlook this kind of a transformation, given it depends on the password itself. So we took a different approach where we revisited the problem and took a totally data-driven approach where we used modern machine learning techniques given we had abundance of data. We built a model that models how users select similar passwords. This similarity model learns the conditional probability of learning W dash given one of the input password of user is W. The goal of the model, the goal was to build a credential tweaking attack using this kind of a similarity model. So the similarity model takes a password as an input and maps it and generates a list of password guesses based on this conditional probability. So now the question reduces how we can build a similarity model of this kind to perform this kind of attack, which is known as a generative model. We used an encoder-decoder architecture that is used in natural language processing for translation tasks. Our encoder and decoder was made using character-level recurrent neural network. We fed our encoder the key-best representation of the password, which then outputs a vector representation, a vector. This vector was then fed into the decoder to generate a list of transformation rules based on the probability. We then applied this transformation rules to the input password to generate our output password. We call this model path-to-path model, and it was trained on 144 million password pairs, and it took 2 days to train our model. So we had this leaked data set, which we divided into 2 parts, the trained data set and the test data set. The trained data set consisted of 144 million password pairs, on which we trained our path-to-path model. We took 100,000 password pairs from the test data set to simulate an online credential tweaking attack setting. In such a setting, the attacker is given one of the password and it has to guess the other password of the user in Q guesses. We selected Q to be less than and equal to 1,000, less than or equal to 1,000. And this is a very conservative number in online setting. We reported the fraction of password that were guessed by different credential tweaking attacks. And we found out that these kind of attacks can be very damaging, as path-to-path was able to compromise around 16% of accounts in less than 1,000 guesses, given it knows one another password, which is 23% more than the prior best work. We also showed that we can increase the efficacy of these kind of attacks if the attacker has access to more than one leaked out password. In this case, path-to-path was able to compromise 23% of accounts, and you can refer to the paper for more details. So we showed that path-to-path is able to outperform all the previous attacks. However, till date, there exists no real-world evaluation of how credential tweaking attacks actually performs on real authentication systems. So we partnered with Cornell IT Security to perform such an experiment. Cornell University has a large-scale authentication system with about 500,000 accounts of alumni, students, staff, etc. It uses credential stuffing defenses and has strong password policies in place. Around 20,000 Cornell emails were present in the leaked data set, and we ran our attack on these accounts to check if they are vulnerable to credential tweaking attack. All the accesses were mediated by Cornell IT Security, and the experiment was performed in a very safe environment. We found out that a total of around 1,300 active Cornell accounts were vulnerable to credential tweaking attack. We informed Cornell IT security about these vulnerable accounts, and these accounts were then put under watch. So now we all are convinced that credential tweaking attack can be severely damaging. However, till date, no defense exists against these kinds of attack. Users often select similar passwords, and to stop users from selecting such passwords, we need to warn users using the current password strength meters. However, existing password strength meters only considers population-wide password distribution and thus are ineffective against credential tweaking attacks. For example, ZXCVBN. Sorry. For example, is it fine? Yeah. For example, ZXCVBN was marked more than 70% of vulnerable password as strong. So now the question comes how we can warn users about passwords that are vulnerable to credential tweaking attack. And one obvious solution is to run audits using credential tweaking attacks, similar to what we performed with Cornell University. But such experiments can be computationally very expensive. And so we introduced the first of its kind personalized password strength meters that are able to detect not only weak passwords, but similar passwords that are vulnerable to credential tweaking attacks. So now we go back to the earlier example where one of Mark's password gets leaked out and the website sends a reset notification to Mark. The website has integrated our PPSM to their system, and so now when Mark selects a password that is similar by replacing the suffix 1 to suffix 123, PPSM stops him by telling that it's a very similar password. PPSM also prevents Mark from selecting a weak common password. Finally, when Mark selects a strong password, it gets accepted. So finally, we come to the question of how we can build such a personalized password strength meter. And an obvious solution is to use path-to-path. But path-to-path are often very difficult to train and are too big and slow to be used in a strength meter. So we took a different approach of using password embedding models that are trained using much simpler feed-forward neural network. So this password embedding model takes input a password and maps it to an n-dimensional vector. If a user inputs another similar password, it gets maps to a point that is close to the previous point. This is because embedding models have the property that two similar passwords get mapped close to one another in vector space. We use this property to build personalized password strength meter that takes into input two passwords and find the dot product of the vector representation of the password. If the dot product is greater than the threshold, we classify these passwords as similar. Using this technique, we were able to detect 96% of vulnerable passwords. Also, this model is very easy to deploy as it takes only 3 megabytes of storage. Also, it only takes 0.3 milliseconds to calculate a similarity score between two pairs of password. So in this paper, we tackled the problem of modeling similarity of human-chosen passwords. We built a password similarity model, and using that, developed the most damaging credential tweaking attack. We also proposed the first ever defense against credential tweaking attack, a personalized password strength meter. Thank you.
Hi, Luke Desautel from Samsung Research America. I may have missed it, but the personalized password monitor or measure, how does it get your previous passwords? You have to trust it with the other password you had? It maintains all of them like a password manager?
Yeah, so there is this whole deployment question of how you can deploy these password strength meter. And one solution can be that users themselves gives input as the other password, or you can integrate it with some leaked password data sets or some services that provides the leaked passwords of the user. So the deployment question is discussed in the paper. Yeah.
So I really like the idea of the password strength meter, but I'm concerned that we're still putting a lot of pressure on the user to just come up with a better password. I guess being personalized, they might not gravitate too much toward the same trends, but is there anything that the server side could do to try to prevent credential stuffing? The only things I can imagine are making sure there's not too many logins coming from the same IP, but that's not ideal either. I guess here you're saying it's the first defense, but I didn't know if you had any other ideas that on the server side, they could try to do some sort of mitigation.
Yeah, one solution is that the server side can run audits, and if it can see that the password is actually being able to be cracked using the credential tweaking attack, which we did, then only change the password. Otherwise, the user can select the password. But these kind of audits are very expensive to run, and that's why we propose to integrate with the strength meter. Yeah.
All right, let's thank the speaker again.